and this is something that I want you to remember for the exam, because I want you to know, how can we represent non-fully controllable systems? Systems for which we got a part that is non-controllable, okay? That means that it escapes. Equations. Let's see what you think about this. Yes, it depends on the chosen basis. No, it doesn't depend. You do not know. What would you bet? What would you bet? Is the name that we give to the engine defining the properties of the engine or not? Very much no. True? Together, the chosen basis is not going to affect the properties of the system. Together, we don't prove it, but the feeling should be there. Change of basis. This is interesting. A system can be written in its control canonical form, and now we are going to see it, if and only if a system is controllable. Let's go. This is, sorry, it comes out as a question, but it's not a question. This is the so-called controllable canonical form, where you write matrix A as its characteristic polynomial, and a matrix B in an opportune way, and this kind of series of one in this way. How do we get this stuff here? If I've got a system that is written in this way, from a transfer function input-output written in this way, y sum dots is equal to minus alpha 1 y in this way it's going to be 2 dots minus alpha 2 y dot minus alpha 3 y plus beta 1 u2 dots plus beta 2 u dot plus beta 3 u. Okay, I'm going to rewrite this ARMA system here into this matrix plus C that is equal to beta 1, beta 2, beta 3. The people that are doing linear systems, you saw it in this way too, with this notation, or the other one? Are you using the flip notation in linear systems?
When we do it, take it from the transfer function.
From the transfer function to the companion form. Are you writing it in this way or with the alphas on the bottom?
I have alphas in the bottom.
My suggestion, okay, for the people that is not doing lean sys, forget about data and forget about these formulas, don't worry. I'm not going to ask you for the exam. I'm going to give you this kind of tip for your professional career. I've got y's and the alphas in this direction. Okay, y from a lot of dots to 0 equals the betas from a lot of dots to 0. Together, let's make an example. Y 2 dots plus 3y dot plus 2y. Okay? Equals to 2u dot minus 9u. You see how you write ARMA models in this way? True that you write ARMA models in this way. And then you might also write them equals to minus, minus, plus. True? Now, look at the arrows. The arrows go from top to 0 and to 0. True? The companion form, as I'm writing it, is done in this way. Alphas, the ones, 1, 0, betas. You see? You see that the arrows of how you write the parameters is concordant. In this way, you're going to remember it. If you do the opposite way, you're going to have something that looks like this. Ones and alphas in this way here. Okay? And this one, 0, 1, 0, 1. And I don't remember if the betas also, I think that also the betas go in this way. Don't remember anymore. But it's kind of more cumbersome. You see? So my suggestion for you is to follow this notation for which you add these, and the ones, and 1, 0. It's going to be, you're not going to beat this. Okay? It's kind of just a tip. If you can write the system in this way, you're going to be able to say that this system is controllable. This is the main point. If you are finding a change of basis for which you get a form that looks like this form here, then you've got a system that is controllable. Can you always do it? No, of course. Proofs for the people that want to go. The algorithm to find the change of basis. And the fact is this one. If we have a non-controllable system, means that I cannot have some subspaces that somehow I can control. And typically, we're going to write them in this way. Subsystem, subsystem, interaction, parts on the B's that go touching this part, C's and D's. And you see that in a certain sense, we have a situation for which this part here, I cannot touch. You see? You see it? I'm doing too fast. This part here is going to be too fast. Whenever I've got some part that I cannot affect, I'm going to be able to write the system up with an opportune change of basis in something that is the one that I'm going to touch, something that behaves in an independent way, okay? And you see how this structure here is an opportune change of basis representation of my original system into part that I can control and part that I cannot reach. Are we together? Are there questions up to now, people? Let's make an example. A equals to 1, 1, 0, 1. B equals to 1, 0. Don't you see it? See? X2 as a scalar in that case was already written in a way that was interesting. Okay. Are there questions, people?
This is not controllable.
Not controllable. This is not reachable. I should kind of edit them in a way that it's always clear with the correct terms, because this depending on this one, if it is that this one has got eigenvalues that are 0 because it's a discrete system, then this becomes controllable in the sense that you can control to 0, but it's not reachable in the sense that this one. So depends on the potency of A to 2, the number of zeros as eigenvalues that it has. We are trying to do too much system theory, advanced system theory now in a small, too little time. Important part for the exam. Important part for the exam. This representation here is a representation that highlights that there are some subparts of the system that I cannot affect with the inputs. Okay? And of course, if I cannot affect it with the inputs, I can do whatever feedback control I want. I'm not going to move the eigenvalues of this part. Do you see it? That means that in a certain sense, from a control perspective, whenever I get a situation like this one, this is a system that I have, and I've got to cope with it. Do I want to change something? I need to add some inputs, or need to change how my actuator injects information. Yeah, actuation, sorry. Together? Okay. We continue tomorrow. Good.